State the law of the conservation of energy. So the conservation of energy is, energy cannot be created or destroyed, it can only be transferred from one form to another. Figure 6 shows a block on a horizontal tabletop, initially held against a spring so that the spring is compressed, which is what we see over here. The spring is compressed by a distance of 0.2 meters, the mass of the block is 0.4 kilograms. The other end of the spring is fixed to a wall. When released, the block is pushed away from the spring. When the spring reaches its natural length, the block leaves the spring and then slides along the tabletop. So, when the spring has reached its natural length, so it's unstretched by that distance of 0.2, the block then has a kinetic energy of 2.2 joules. A constant frictional force acting between the moving block and the tabletop eventually brings the block to rest. So it moves a distance of 1.2 meters, the frictional force slows it down, it eventually comes to rest. When the block leaves the spring, the block has a kinetic energy of 2.2 joules. The mass of the block is 0.4 kilograms. Calculate the maximum velocity of the block. So this is straightforward. We're just using kinetic energy is equal to a half mv squared. Speed is then equal to the ke times 2 divided by mass square rooted. Square root of 2 times 2.2 over 0.4. which gives a velocity of 3.3 meters per second. The block travels 1.2 meters after leaving the spring before coming to rest. Show that the frictional force between the block and the tabletop is about 1.8 newtons. So we can use for this question, work done is force times distance. The distance is 1.2 meters. The work done is the work done by the frictional force, and that work done will decrease the kinetic energy from what it was before, 2.2 joules to 0. So the work done would be 2.2 joules, and then F in this case would be the frictional force, so that will be the work done over distance, 2.2 over 1.2, which is 1.83 recurring. The spring was initially compressed through 0.2 meters. The constant frictional force acts on the block whenever it is moving. Calculate the elastic potential energy in the spring when in its initial compressed position. Assume that the spring has negligible mass. State an appropriate unit. Okay, so we want to work out elastic potential energy. There are two equations for this. E is equal to a half kx squared and a half fx. But if we look at what we have in the question, we don't have the spring constant. We're not given that anywhere. Nor are we given the force in the spring. It's a common mistake in this question to use the frictional force here, but that's not what this F represents. This F represents the force in the spring at a particular compression or extension of x. We don't have that force. It's not equal to the frictional force, so actually we can't use either of these equations. So we're going to have to use energy conservation to solve this. So let's think about what energies we have before and after this event. So going up to the diagram, initially we have elastic potential energy. Over here, we have elastic potential energy. The block then moves, and as it's moving, there is work done due to friction. At this position here, the block has a kinetic energy of 2.2 joules. At the end, there is no kinetic energy. All of the energy has been transferred to heat in the block and in the table because of the frictional force. So actually, the energy partway through the motion, block has a kinetic energy of 2.2 joules, is not relevant. We can look at the energy before and after. Before, all of the energy is elastic potential energy. Afterwards, all of the energy is heat in the block and in the table surface because of the work done by the frictional force. So, if we equate elastic potential energy to the work done by the frictional force, we can work out elastic potential energy. The work done by the frictional force would be that frictional force we calculated of 1.8 newtons, or 1.833, multiplied by the total distance, which was 0.2 plus 1.2. Not just the 1.2, you have to also include the 0.2, as throughout the motion of the block, it's experiencing that frictional force, and that frictional force is consistently taking away energy from the block. So the work done by that frictional force, work done as force times distance, is the 1.833, etc., multiplied by the total distance of 1.4, which gives us an energy of 2.56 recurring. So that would be 2.6, its energy, so the units would be joules. So again, all of the initial elastic potential energy gets dissipated as heat because of the work done due to friction. And the final part, the force exerted on the block by the spring is proportional to the compression of the spring. So that's basically saying F is equal to kx. Calculate the maximum force exerted on the block by the spring. So again, we don't have the spring constant, so we can't use F is equal to kx, but we now have the energy stored in the spring, so we can use E is equal to a half Fx. When the spring is compressed by a distance of 0.2 meters, the energy stored was 2.56 recurring joules, and then so we can just rearrange this for F. F is equal to 2e over x, which is 26 newtons.